Biomolecules. Organic compounds present in living organisms are generally called biomolecules. Some of the biomolecules which we shall discuss here are carbohydrates, proteins, enzymes, hormones, vitamins, and nucleic acids. Carbohydrates. Carbohydrates were once considered to be hydrates of carbon, since they got easily dehydrated by concentrated sulfuric acid to form residual carbon. They were even given a general formula like glucose C6H12O6 can be expressed as C6H2O 6 times. But formaldehyde, which is not a carbohydrate, can also be expressed as C1H2O once, which became absurd. Therefore, a new definition was considered. Carbohydrates are optically active polyhydroxy aldehydes or ketones, or the compounds which produce such units on hydrolysis. Carbohydrates classification. Carbohydrates are classified based on hydrolyzed products. Monosaccharides, oligosaccharides, and polysaccharides are these. Monosaccharides. A carbohydrate that cannot be hydrolyzed further to give simpler unit of polyhydroxyaldehyde or ketone is called a monosaccharide. I'll repeat. A carbohydrate that cannot be hydrolyzed further to give simpler unit of polyhydroxyaldehyde or ketone is called a monosaccharide. For example, glucose and fructose. About 20 monosaccharides are known to occur in nature. Oligosaccharides. Carbohydrates that yield 2 to 10 monosaccharide units on hydrolysis are called oligosaccharides. I'll repeat. Carbohydrates that yield 2 to 10 monosaccharide units on hydrolysis are called oligosaccharides. Example, maltose and sucrose. Among these, the most common are disaccharides. The two monosaccharide units obtained on hydrolysis of disaccharides may be same or different. Polysaccharides. Carbohydrates that yield a large number of monosaccharide units on hydrolysis are called polysaccharides. For example, starch and cellulose. Classification based on functional group. Aldehyde or ketone. Aldose. Monosaccharides which are having aldehyde group are called aldoses. Example, glucose. Ketose. Monosaccharides which are having ketone group are called ketoses. For example, fructose. Classification based on carbon atoms. Number of carbon atoms. Triose, tetrose, pentose, hexose, heptose, etc. So a triose means monosaccharides having 3 carbon atoms. Tetrose having 4 carbon atoms. Pentose having 5 carbon atoms. Hexose having 6 carbon atoms. And heptose having 7 carbon atoms. So we just combine the classification based on the functional groups and the carbon atom numbers in this manner. So we segregate, we just see that carbon atoms, general term, aldehyde and ketone. If there are 3 carbon atoms in the monosaccharide, it's called triose. If there is an aldehydic functional group, you call it to be aldotriose. If it is a ketone, you call it as a ketotriose. Similarly for 4 carbons, 5 carbons, 6 and 7. Glucose. Molecular formula C6H12O6. Molecular mass 180. Glucose is an aldohexose and is also known as dextrose. It is the monosaccharide of many of the larger carbohydrates, namely starch and cellulose. Preparation of glucose. We shall see a laboratory method and a commercial method. From sucrose, cane sugar. When sucrose is hydrolyzed by boiling it with dilute hydrochloric acid or dilute sulfuric acid in alcoholic medium, glucose and fructose are obtained in equal quantities. From starch, a commercial method. When starch is subjected to hydrolysis by boiling it with dilute sulfuric acid under a pressure of 2 to 3 atmospheres and at a temperature of 393 Kelvin, glucose is obtained. The elucidation of glucose. We use various reactions to test the structure of glucose. When it is treated with hydrogen iodide upon heating, it gives normal hexane or a straight-chained hexane. This tells that there are 6 atoms linked in a straight chain. When reacting with hydroxylamine, it gives glucose oxime. It's a typical reaction of carbonyl compounds. When treated with hydrogen cyanide, it gives glucose cyanohydrin. These two reactions confirm the presence of carbonyl compounds. When treated with bromine water, a very mild oxidizing agent, easily oxidizable aldehyde can be oxidized, giving gluconic acid. So this confirms the presence of an aldehydic group. So since, according to the definition, glucose is a polyhydroxy compound, so we wanted to check how many hydroxy groups are present. Usually we do it by esterification with acids. So we are taking here acetic anhydride. For every mole of glucose, 5 moles of acetic anhydride are reacting to give glucose pentaacetate. So this confirms the presence of 5 hydroxy groups. So if there are 5 hydroxy groups, oxidizing agent like dilute nitric acid, which will oxidize both the aldehydic group and any primary alcoholic group present. So this gives glucaric acid, so which confirms the presence of one primary alcoholic group. And therefore, we conclude that glucose has a straight chain 5 hydroxy groups containing aldehyde. So we have got here the Fischer projection. The Fischer projection of glucose. It's an open chain. So this glucose is generally called as D plus glucose. This because with reference to the structure of glyceraldehyde, that is, all those compounds which can be chemically related to a dextroisomer of glyceraldehyde are said to be D, and all the compounds which can be chemically related to a levotetraisomer of glyceraldehyde are said to be L. We can generalize if the OH on the penultimate carbon is on the right, then glucose is D configuration. If the OH on the penultimate carbon is on the left, then the glucose is L configuration. Cyclic structure of glucose. The open chain structure of glucose explains most of the properties but not the following. That is, it does not give positive Schiff's test and also sodium bisulfite test. The pentaacetate of glucose does not react with hydroxylamine to form oxime, indicate absence of aldehydic group. Existence of 2 forms of glucose, that is alpha and beta isomers, is not explained by the open chain. The above observations are due to existence of hemiacetal structure of glucose, which is 6-membered ring in which OH at carbon 5 is involved in ring formation with carbon-1 cyclic structure. Carbon-1 links with carbon-5 via an oxygen atom, thereby forming an hemiacetal structure. Therefore, we get here the alpha isomer and a beta isomer. In these Haworth structures, if the OH on carbon-1 is present below the ring, then it is called as alpha isomer, and if the OH is present above the ring, it is called as the beta isomer. So two cyclic hemiacetal forms of glucose, the two cyclic hemiacetal forms of glucose that differ only in the configuration of the hydroxyl group at carbon-1 are called anomes of glucose. They are also called pyranos because the Haworth structure are similar to the organic compound cyclic structure of fructose. It is a ketohexose with molecular formula C6H12O6. The ketonic group is present at carbon-2. It is a D-isomer and is levorotatory. It is a ketohexose with molecular formula C6H12O6. The ketonic group is present at C2. It is a D-isomer and is levorotatory. The Haworth structure of fructose is known as furanose, where carbon-5 is linked to carbon-2 through an oxygen atom. So fructose is similar to organic compound furan. We've got here the structures of pyran and furan. Sucrose. It is a disaccharide. So we'll look into a couple of disaccharides. The first one is sucrose. On hydrolysis, sucrose gives equimolar mixture of alpha D plus glucopyranose and beta D minus fructofuranose. Glycosidic linkage between carbon-1 of glucose and carbon-2 of fructose. It is a non-reducing sugar because of the absence of free carbonyl group. Invert sugar. Hydrolyzed product of sucrose which brings about a change in the sign of rotation from dextro to levo rotation. This is because on hydrolysis, sucrose gives the mixture of dextrorotatory glucose of plus 52.5 degree rotation and levo-rotation of fructose of minus 92.4 degree. Maltose. On hydrolysis, it gives 2 units of alpha D plus glucopyranose. Glycosidic linkage is between carbon-1 of one glucose and carbon-4 of another glucose unit. It is a reducing sugar because of the presence of free carbonyl group. Lactose. Known as milk sugar, on hydrolysis give 1 unit of beta D-galactose and 1 unit of beta D-glucose. The glycosidic linkage is between carbon-1 of galactose with carbon-4 of glucose, which is beta in nature. It is a reducing sugar because of the presence of free carbonyl group. Note: the linkage between two monosaccharide units through oxygen atoms is called as glycosidic linkage. Polysaccharides. These are the carbohydrates which on hydrolysis give more than 10 monosaccharide units. Example: starch, cellulose, glycogen, etc. Starch. Polymer of alpha D glucose units and consists of 2 components, amylose and amylopectin. Amylose. Amylose is water soluble, long, unbranched chain of alpha D plus glucose units held by carbon-1, carbon-4 alpha glycosidic linkage. You call it as C1C4 alpha glycosidic linkage. Constitutes about 15 to 20% of starch. Amylopectin. Amylopectin is water-insoluble, branched-chain polymer of alpha-D-glucose units, held by C1-C4 alpha-glycosidic linkage. Branching occurs by C1-C6 alpha-glycosidic linkage. It constitutes about 75 to 80% of starch. Cellulose. It is most abundant organic compound in plant kingdom. It is a predominant constituent of cell walls of plant cells. Straight-chain polysaccharides of beta-D-glucose units joined together by C1-C4 beta-glycosidic linkage. We come to glycogen. The carbohydrates are stored in animal body as glycogen. It is also called as animal starch because its structure is similar to amylopectin but highly branched. It is present in liver, muscles and brain of animals and also in yeast and fungi. It will be broken down into glucose by enzymes when body needs glucose.